Alright, so tonight, just a follow up from the other night. It's not going to be very long, I don't think, but we'll see. So, covariance is defined to be this: the covariance between x and y. Again, it's the strength of a relationship between the two of them. Okay, is defined to be the expected value of x minus its mean. I'll write mean of x like this, times the expected value of y minus its mean. And you're like, well, what does that come out to be? Well, it turns out it's this, right? It's the sum, the double summation, and we'll write it like this. We're going to go xi minus mu x, and we're going to sum that up from 1 to n. And then this is how the big kids will do it. They'll do yj minus mu sub y, and then j's go from 1 to m or something. They do that because they don't have to have the same amount in each column. Okay, that's how it typically will be done. And then, of course, times our joint density function. Okay, now what would that look like if it was continuous? You know what it would look like if it was continuous. Don't be ridiculous. You're going to integrate over the entire region. And of course, it would be literally this: x minus mu x times y minus mu y, and then times your f of x and y. And then dx, dy, or dy, dx. Yeah? Exactly like before. Okay? Now, I'm going to work this out for you thinking there is a shortcut. Of course, there's a shortcut. So, the way this works is this. Again, it's the summation, the double sum. And I'm just going to kind of cut to the chase here like that. It's x minus mu, y minus mu. This is mu x, this is mu y. Okay, let's FOIL that out. You're going to get xy minus x mu y minus y mu x, and then minus mu x mu y. Now I want to double sum that whole thing. Okay, well then I can pass it through, right? So I can pass those through and take a look at what's happening there when I do that. Okay, so if I pass it through, well, probably just gonna leave this alone, right? And then minus this guy, and the person might say, well, Mr. Groom, oops, this is all times f of x and y. Forgot my marginal there. Whoops, that might be an issue. Minus, and I'll pull the mu y out front because, again, with respect to x, it is a constant. With respect to x and y, to be quite honest with you. Okay, minus, and then this is the same dealio. The mu y come out, or the mu x come out front, rather. And then double summations of y, f of x and y. And then minus mu x, mu y, double sum f of x and y. Okay, well, let's start with the obvious. This thing right here, what is the double sum over the entire integral? Well, it's 1. So it's minus mu x, mu y. Okay? Now, this part up here, this part, what would you expect it to be? Well, we'd probably expect it to be the expected value of x and y. Okay? That's what that would boil down to. If you think about it, it makes perfect sense. It's literally what it would be if this was just an x times f of x. That's what you'd call that. You'd call it the expected value. Expected value of both x and y is what we'd call it, however. Okay? And then, so if you look through this mess here and you're like, well, okay, well, what does this say to me? Oh, this is plus, by the way. What does this say to me right here? Well, if you look at this bit right here, okay, remember, it's x times this guy. So let's look at just this piece right here. What would x times that guy give you, do you suppose? Yeah, oh, mu x. You're right. Good job. So it's minus, and this is mu y. Now remember, you've got a double summation yet. So, but this part here is going to be mu x, and then this double sum, or this other summation, is of 1 f of x and y, right? Because in other words, we took the x out of there. All that's left is a 1. And what happens if you integrate, or if you double sum what's left over here? Now, if you double sum that up, it's going to be just. It's just going to be 1. Okay, that's what that boils down to. Now, The next guy's going to be the same deal, of course, mu x, mu y this time, however. And then, of course, this guy is a plus, so I'll bring him down, mu x, mu y, like so. And so one might be tempted to think that, hey, the shortcut method is just simply the expected value. These guys cancel out. The expected value of x and y minus, this is the expected value of x times the expected value of y, yes? That is by definition covariance for a discrete distribution. Okay. Now, we will look at this in a minute. We'll do one of these guys, kind of see how it goes. All right. Got to play it by ear a little bit there. But again, we'll just kind of play that by ear and see what happens across there. Now, I'll pause for a second, get on a new page, and get that kind of set up for us. So I'll pause you and be right back. Okay, so here's a chart that depicts some outcomes. You can think of it as rolling two dice. Maybe this is X is up here. These are the Y's over here. The idea being is that you do X and you do Y. If it was completely independent, we would see the same sorts of things happen in each direction. And let's see what that is. If I add this direction across, this is well, that's 4 20ths. 4 20ths is 8, 9 20ths here, and this is 1/10, and that's 1/10. That's 2/10, which I'm gonna write as 4 20ths if that's okay with you. And then this guy here had better be 7 20ths, I guess. So this would be 2 20ths and 2 20ths and 3 20ths is 7 20ths, because that better be everybody. And we can also add down the columns. This is 2, 4, 8 20ths, I guess. And this is 2 20ths, 4 20ths, 6 20ths. No, 2 20ths, 4 20ths is 6, 7 20ths. And so the other one better be 5. Well, that's, yeah, 5 20ths. Beautiful. Okay, there they are. Now, think about this for a minute, friends. Okay, what would the expected value of x be here? Well, how would I do that, Jay? Well, let's think about it now. The values for x are 1. There's an 8 out of 20 chance I'm going to get an x, yes? And there's 2, and then there's a 7 out of 20 chance I get a 2. And then there's 3, and I get a 5 out of 20 chance I get that guy. So if I do this, again, we said it's all out of 15, so 8, 22, 37 20ths is my expected value for x. My expected value for y is similar, but of course different. So that's 9, 8, 17, 21 is 35 20ths. Okay, so that's pretty easy. You're like, oh, I can totally do that, Jay. I know. Right. No, I know. So you do that. It's so if you're thinking about this, you're like, well, how would I find this guy? Well, I need the expected value of x and y minus the expected value of x times the expected value of y. Well, I got this. This is simply 37 20ths times 35 20ths. Okay, that part's easy. But how do I find the expected value of x and y? How would I pull that off? Okay. One moment, please. Excuse me. All right, now, to find the expected value of x and y, what are we going to do? Well, we're going to come back up here to our stupid chart if I can find it, because the stupid computer hates me tonight. There we go. So the expected value of x, y. What do you mean x, y? I mean x times y. So 1 times 1 is 1, right? But look, I'm going to multiply that by its probability. Plus, and I'm just going to go across the top. It's going to be 2 times 1 is 2 times 1/5. plus 3 times 1 is 3 times 1 20th. And now let's come across the middle here. It's going to be 2 times 1 is 2 times a 10th. Plus 2 times 2 is 4 times a 20th. That's going to be 6 20ths. And 3 tenths. Plus 6 tenths. Plus 0.1, oh, why did I do that way? 9 times, that's actually 3 20ths. I'm going to do it that way. So that's a fifth, and then 2 fifths, and then 3 20ths, and then 2 tenths, and 4 20ths, 6 20ths, 3 tenths, 6 tenths, 27 20ths. So if they're all in terms of 20, this is 4, and this is 8, that's 12, 15, 19, 23, 29, 56, plus 12 is 68, plus 6 is 74 20ths. So it sure looks like it ought to be 74 20ths. So if I do the math on this guy, and I'm just going to get a calculator, it's too late in the day to do that all by hand. I was going to do it all by hand, I just don't care anymore. I was really trying to impress Caleb, but I don't know. I don't care, Caleb. I don't care, I'm not doing it anymore. So I just did 37 times 35 divided by 400, same thing. So 37.888. 37/88 is our covariance. Guys, our covariance. Give me the old decimal Rooney on that fella. Oh, give me the decimal, I say. About 0.4625, okay? Come on, stop it. 0.4625. Okay? Now that is the covariance of the x with the y. Okay, that's how it would work in that particular situation. And it's pretty straightforward, pretty easy to do. Now, really what I really have here is I have x's and y's. That's all I have. Because it's in this chart notation, that's how it would have to work. Okay, now, another way that you'll see it show up sometimes is done up this way. Not like that, I already did it that way. Is you'll have a chart of data. And often this is the most obvious or most important way of looking at these covariances. Not always, but a lot of times. These are my x's. I'll go ahead and label them as x's. X, y. And here's just some values I'm making up for x's as I go. Cool. And then I'll make up some y's. I'm going to make this thing a negative core. Oops, no I'm not. I was going to. There we go. Cool. So clearly as x's are getting bigger, y's are getting smaller. What does that mean to me? Well, it means to me that I'm going to have a negative covariance here in a minute. Before I do that, I need to find the average of both columns. And I'm going to go ahead and find the variance of both columns just for a good time too. So this dot P routine. Boom. Boom. Now remember, it's the x minus the mu times the y minus its mu. So what I'm going to do is I'm going to say equals x minus I'm going to click on this fella here, but I'm going to go ahead and hit the F4 a couple of times. And if you do it right, oh shoot, oh knock it off. Boy, she's not happy with me now. Boom. And then function F4. And I want it to stay like that because I want it to be staying in row 10 when I drag it down. So I just copy and drag this baby down. See if that's right. Look at one of these guys. Yeah, that's right. That's what I wanted to do. Now you can copy and drag this whole thing sideways if you like. And it should, in theory, work. Yep, that's what I wanted. Beautiful. So these columns represent x minus mu and y minus mu. So at this point, what I'm going to do is I'm going to come over here. This is a 1, 2, 3, 4, 5, 6, 7 column matrix like that, 7 row matrix. So I'm going to create it over here, a 7 row matrix. Oops. 7 column matrix, I mean. And make sure I get that right. Over to 7, yes. Okay, and I'm going to say equals transpose. Oftentimes, and I'm going to show you in the computer in a few minutes, how you can get what I'm going to show you right now in a different way, quite honestly. Now, you have to Control Shift Enter to do what I'm doing. Boom. It just transpose the entire matrix. It treats it as one unit when you do that. Now, I'm going to highlight an area like this, and I'm going to say equals m mult. That's matrix multiplication. And I'm going to take this transpose matrix over here, comma, this guy here. I'm going to multiply those two matrices together. And then I'm going to divide by the number of terms I have, which is 7, or 7 pairs of data. Control Shift Enter, right there. And so if I look over here, look at that, will ya? There's my variance for my x's. It's right there. Hey, there's my variance for my y's. Jesus, right there. How about that? Hey, what is this 38 crap about? This negative 38? Yeah, friends, that's your variance. And this right here has a special name. This guy is called the variance covariance matrix. And it's kind of a big deal. It shows up a lot, and you will see it from time to time in industry and whatnot. The cool thing is you never have to. I didn't try. Oh shoot. Anyway, I was going to write it, but apparently I typed it on top of it. So variance covariance matrix. The variances will always be on the diagonal. Jay, even if there is more than 2 variables. That's correct. You mean if there was 3 variables, I could do the same thing I just did. That's correct. I'll show you momentarily. It's pretty key. But anyway, we'll never really have to do it this way. Okay, that's not how we do it anymore. So nowadays we have a built-in solver in Excel. If you want the variance covariance matrix, you just literally click on covariance. It says, where's your input range? That's this data right here. Notice I don't have to do that in-between step of subtracting mu. And I don't have to do that because the computer has already been programmed that, oh, I need to do this covariance. It says it has to go in and do that subtraction bit itself. And there you go. Now you see that they do not include that other one up there because those two always match. That's pretty typical of a variance covariance matrix. They will not generate both of them at the same time. So here I'm going to make up some z's, if you will. And so if I had 3 terms doing their thing, one can see that these guys are getting bigger. So, you know, x and z are going the same direction. So they're going to have a positive correlation. They're going to have a positive correlation too. But they're going to have a positive covariance. But x and y were a negative covariance. That will also be true for for y and z. So I'm going to go ahead and do what I just did here a minute ago with these guys. I'm going to drag them sideways, whatever. Bam. I'm going to go ahead and put this right here. I'm going to go equals. No, I'm not, you liar. You're going to do this, and you're going to drag it sideways as well. Sweet. That's correct. Nice. So then I'm going to go down here. I'm going to do a 3 or a 7 by 3, or 3 by 7 rather. There it is. Equals transpose. And again, this is how we would have done it back in my day, you young whippersnappers. Divided by 8, or 7 rather, I mean. And there they are. Ah! Oh. Oh, let's try that again, stupid. Okay, we're going to highlight a 3 by 3 matrix, and we're going to say equals m mult, moron. Let's try that again. I apologize. It's been a long day. Man, it's been a long day. Wow, has it been a long day. Okay. Oh, you know what I didn't do? Oh, no, never mind. Darn it, that was actually right, Jay. No. Okay, never mind. I got ahead of myself. There we go. We're good now. We're good. I'm still paying attention. And no, I'm not drunk, in case you're wondering. No. So equals this fella, comma, this guy. By the way, this is why you go ahead and use a computer when you're doing when you're doing Control Shift Enter. Bam. Anyway, if we didn't screw it up, which I very well may have done. Something went haywire. No, this is wrong. Okay, let me pause for a moment, then I'll catch back up with you. Oh, I swear I did it the first time, but I was wrong. So there it is. There's the variance for x's. There's your variance for y. There's your variance for the z's. Again, variance, remember, is the change, the variation within the x's themselves. They're never going to be perfect. Of course, they're going to vary out and back and forth around the mean. Now, here's the variance of the y's with themselves, the variance of the z's with themselves. This correlates to, this is the first row, first column, second row. Well, first column, second row, if you think about it, first column, second row, why, that is the x's with the y's. And this is the x's with the z's. This right here, of course, is the x's with the y's, the x's with the z's. And these are just repeats. And of course, these are y's and z's and y's and z's. And again, I can get that same information simply by using the Covariance tab. You can also simply go in and click in equals covariance. I would not do that. I would not do it this way, to be honest with you, though. I would not. I would personally go in and use that covariance generator in the data functions. That's what I would do, but you could do it one at a time. Typically, we go find the variance covariance matrix, and we're done. So with discrete distributions like that, that's a pretty sweet way to do it. Now you're like, well, what if it was a discrete distribution, or a discrete? Just did discretes, Jay. What if we did? What if we had a continuous distribution? Well, that's a good call. So it would be the double integral. Okay, so I need to find the expected value of x, y first, obviously. And how would I do that? Well, I've got the joint distribution, of course, some f of x and y. And so I'm simply going to multiply by x minus mu times y minus mu. It's mu, of course, x mu and y mu. And then integrate this sucker all the way from here to here. Okay, so let's just say, let's suppose that f of x and y is equal to I don't know, e to the negative x I'm going to make one up here because I just didn't think to make that up ahead of time. So I'm just going to make one up here. I don't know what this is going to be, so what I'm probably going to do is just do a double integral of some function that I like and then just solve for my whatever my constant would have to be to pull off the function I want to use, okay? Y comma x comma, I'm going to go 0 to, I'm just going to put this in for infinity because that's good enough, and then comma, oops, it should be, no, you dummy, it should be x, and this should be, again, this should be close enough, and then y comma 0 comma and voila. Come on, Betsy, give it to me. Actually, you know what? I won't do that. I won't do that. Yeah, so that's true. Let's just pick a function that I know will integrate 3x plus 2y. And again, let's just say this function is on the interval from 0 to 2 and 3 to 5. That is its interval of operation. So I'm going to put a big fat A in front of it instead. Remember, this is how your book will always write it, like this, because it goes from infinity to infinity. It's just a better way of writing it. So actually I'm going to do that. I think it's just going to be an easier problem for us to do. I didn't want to do the other one anyways. Alright, so double integral. I'm not going to put the a in there. I just don't care. We'll put that in later when we're all done. So comma x, comma 0, comma 2, comma y, comma 3, comma 5. So 44. So a is 1/44. There we go. Cool. So what I'm going to do is this. Negative infinity to infinity. Not negative infinity to infinity, you dummy. Double integral. And I'm going to pull that 1/44 out front. So I'm going to replace this with just 3x plus 2y right there. Now, what is x minus mu? Well, how would I find mu? All right. Well, x minus mu, or the expected value of x, rather, I should say, for this guy. How would I find the expected value of x? The expected value of x is going to be the double integral, okay, of our f of x and y, like that, right? Like so. And then here's the deal. I'm going to do dy over its entire, and there's going to be x in here. Sorry about that. So I'm going to integrate dy over its entire region, 3 to 5. And dx, I'm going to integrate it over its entire region, which is 0 to 2. So let's see what that happens here. So I like to cheat on these guys. Notice I don't have to change much, except obviously I need to put that 1/44 out front because, you know, there's that. And then, so right in here, I'm going to put in x times parentheses, like that. So 12/11ths. 12/11ths. Expected value of y is ditto, except y times this fella. So all I have to do is go in and change one thing, change that x to a y. And I get 134/33. 134/33. Okay, so back up to here. So I'm going to do this piece right here in a second. So when I do this guy right here, the expected value of x and y, we'll figure that out in a minute. I'm going to do down here though. So I know that I have correlation of x and y is equal to the expected value of x and y, which we'll get to in a minute, minus the expected value of x times the expected value of y. Okay? That's it, friends. And so when I do these double integrals like this, just kind of keep that in mind when we go through them. It's almost kind of fun. Okay? Ouch. Let me pause for a sec here. I'm sorry, it's Friday night. I was getting a little off kilter with myself. I knew I did something wrong. Here we go. Yes, that in theory could work, but let's do it this way. So I found those values. So let's come back to the top. So we're going to take x minus 12/11ths times y minus 134/33. And then let's times by that guy, and let's then do our dy dx. Good grief, I'm sorry, what a weird day. Here we are. So then you'll notice all I have to add is those minus bits there. So come back into here. So you want to find the expected values. You just go minus 134 divided by 33, parentheses. I'm just going to do it the other way around, times x minus 12/11ths. What? What? Oh dear heavens. Negative 2 363rds. Negative 2 363rds, which is a very small negative covariance. Okay? Which brings up an interesting point. What if two variables have a covariance that is equal to 0? Well, that means they don't covary at all. They don't jump around at all. Wait, what kind of functions, what kind of variables don't change with respect to each other? Independent ones. That's right. And so in general, this is always true. Independent variables will have 0 covariance. There's once in a while you can have a 0 covariance, but remember that's a linear covariance, okay? So once in a while you could have functions that have a very strong They have some covariance there, but not a linear covariance. In other words, they might very well fit a quadratic function, but they don't fit a linear function. And so as a result, you will not end up with a any covariance at all. Now, one more thing, and this is the last thing, really. Well, there's one more little piddly thing, I guess. The correlation between x and y is always given by this. It's the covariance of x and y divided by the variance of x, or the standard deviation of x times the standard deviation of y. Okay, now that's a little tricky. People will kind of mess that up sometimes. So if you come back over here, my nose. I'm going to look at this piece right here. If you don't mind that covariance matrix, I'm going to go ahead and copy that guy and paste it somewhere. Because I just want to show you this. If I right click, copy that baby, and paste. I'm just going to paste the values is all I want to do, okay? Now, those are the variances and the covariances. Oh, that's nice. So, but here's my question then. Well, what happens when we do the, what would happen if I divide this thing out and found our covariance here? I mean, our, what I want to say, our correlation. So we have right now negative 38.3673. But we're going to divide by, the square root of this guy here, which is, that would give us the standard deviation of x, times the square root of this guy. And if we cross our fingers, we'll get a correlation of negative 0.894. That is a very strong correlation, okay, which we're not terribly shocked by. 38 is a pretty good sized covariance. Now, a person could do equals coral, like this. And what you can do is you can go in and click this guy here, comma, this guy here, and you can actually get the correlation from that. And you'll see it's negative 0.8941, yes? Yeah, 894, yeah, sweet. Now, you can also make a correlation matrix. And so when you do that, what you'll end up with is the correlation will be here and here. And then these guys here should be 1 and 1 when you're done. But as a general rule, I don't really make a big deal about that. Correlation matrix, like I was noticing that I've seen guys who do stock market analysis use that a lot. It's just a different step. It's basically taking the covariance variance matrix and switching it out to make it a correlation matrix. Okay, but correlation's a big deal. You may have seen this back in the day. Some people have seen this probably. Here's my x's and y's. I can make a scatter plot of them. And this is probably where you've seen correlation before. Right click, show trend line. Hey, let's show the equation and show r squared. Well, there's r squared. But remember, if you do the square root of r squared, you will get r. Duh. Bam. And you'll notice it's 0.89398, which is basically that. This is obviously rounded off, so this will be rounded off. But you have to be smart enough to know, hello, that line's going down, so it has a negative correlation. If it's going up, you have to say it's positive correlation. Okay? So there's that. And then I think the last thing I wanted to mention, and it's pretty straightforward. I think you'll see it's pretty obvious there. But what happens to correlation when you multiply your x's and y's? You know, we talked last time that the variance is affected. The variance is affected when you do ax plus by and all that. But what happens to the correlation if you square them and move them around? Okay, and so we'll talk about that just briefly here. If I can find the right freaking page, it'd be nice. Anyway, we can talk about that. You can kind of see it yourself. No problem. What happens here? Will it be any change at all? Is I guess what I want to say. Think about this. So grab these x's and y's. If you grab them, copy them, paste them over here. Okay. What would happen if I took and multiplied equals this guy times 2, drag it down for instance, and this guy here, times, let's say times 3, sure, And then see if we can find a pattern here. See if there is. Do you think there's a pattern between the two of them? I don't know. Right click. I can do it a couple ways. I'll do this correlation equals coral of this one, comma, this one. What? Wait, what? Wait, what? And so, interestingly enough, when you multiply them through, what happens to the correlation? What, is that always true, Jay? Well, what happens if I made this 10, let's say? Okay, it will not change if you make them both positive different. You see what I'm saying? What would happen if I took and subtracted? So if I did equals this fella minus, I don't know, minus 10 just for a good time. So you're thinking this one won't matter, and you're right, it won't matter. And why is that? Because all I did was I kept the same pattern, I just shifted them somewhere. Plus 20, let's say. One would think that if there was a solid pattern before, there's going to be a solid pattern afterwards. The only difference, of course, being is what it looks like. I actually did it this way. Equals coral. This one, comma, this one. What? No, I know, right? The only time it might have a problem is if what? If you multiply one of these dudes by -1. There are negative values. If I multiply this by -10, what will happen? Nothing happened! Isn't that cool? Isn't that pretty impressive, friends? Now, why? Why didn't that happen? Because if you think about it, in this case, they went up. These guys went up. And these guys went down. Wait, what happened here? Wait, what? Wait, what? So, oh, there it is. So, wait, I know what happened. It did happen what was supposed to happen. It freaked me out for a minute. I'm like, what? There we go. So remember, in the first set we had a negative correlation. Here we had a negative correlation. Notice that in both cases, this case here, our x's, you see this, are getting bigger, and our y's are getting smaller. Do you see this? That's why it's a negative 0.8941. Here, my x's are getting bigger, and my y's are getting, what are happening to my y's? My y's are also getting bigger. That's why it's positive. But you'll notice that it is within decimal points. You see 0.894, 0.89401. I'm not really sure why that one didn't round, unless this column is maybe just a skosh wider. I wonder if it's just a skosh wider. I think it's just a skosh wider. Oh, I know why. It's not because it's a skosh wider. It's because it doesn't have to account for the negative sign that this one does. These guys are the same. They're the same. So the idea is they're the same relationship, except this one in the middle, the x's and y's are both getting positive. So here's the idea. It doesn't matter what you multiply your x's and y's by, as long as they're the same sign, the correlation will not change. If you add or subtract to both of them, and as long as you don't change, as long as you don't change the direction there, they will go there. The only way it'll change is if you multiply one of them by a negative constant. You will flip the sign on the correlation. Okay. And by the way, it'll also change the sign on the covariance. So you can do covariance here. Covariance of this guy. Oh, you idiot. Try again, dummy. This guy, comma, this guy. And lose the B7 there, stupid. Bam. Wait, that's what it was on the previous page. Yes, I'm well aware of that. Equals covariance. Oops. Jay, does it matter which way you say covariance? Does it matter if you do this guy and then this guy? It does not, actually. But you'll notice that this one comes out to be... Uh-oh, what just happened here? Okay, now I just said it didn't. Why are you bothering me? It should not matter. Okay. Wait, what? Wait, what? Interesting. Wait. You're like, wait, Jay, you lied to us. Oh, I didn't lie to you. What I was getting at is, what's the difference between these guys? Notice that the correlation doesn't change. The correlation here and the correlation here don't change because all we did was what? All we did was shift it sideways, yes? So the variation, each one of their correlation, their standard deviations didn't change. However, the one in the middle here did. So watch me do variance of P here for this guy and for this guy. And watch me square root both of those. And watch me take and do equals this guy divided by this guy times this guy. What? Exactly, friends. And that's why we like correlation usually a little better than covariance. Because covariance can really kind of throw a person off when they see it. It kind of freaks you out. You're like, it was 700, Jay. That's weird. It was only 38 a minute ago. Well, that's true, but look at your y's, for goodness sakes. Your y's went from being 80 to 800. So we've really spread the data out. So we really just have changed the y's. So we've really changed the variance or the standard deviations on the y's, and as a result, we've really blown up our covariance. However, when we divide it back out, you'll see that the actual correlation didn't change. Okay? So we'll talk more about correlation going forward, but this is the first time it's kind of introduced in this class. Anyway, I hope that helps. Again, I think it's really helpful if you look at data more than if you look at just theoretical explanation of things sometimes. So, all right, let me know if you need help. Bye.